Today I am going to present a seminar on topic of random process, which is an important concept in probability theory and communication engineering. A random process, also called as a stochastic processing, is a collection of random variables indexed by time. In simple words, process outcome is not fixed. It varies with time in an unpredictable way. Example including noise in electronic circuits, stock markets variations, temperature variations, wireless channels, reading. Random process helps engineers model the uncertainty present in real world systems. Key terminology. Before understanding random process, some important terms: a sample function, one possible realization of the process over time. Assemble collection of all possible sample functions. State space. All possible values the process can take. Time domain. The index set over which process is over. Deterministic versus random. Deterministic signals are predictable. Random signal varies irregularly. Sample function a single realization. Sample function. A random process is a collection of random variables are indexed by time. This means the value of the process changes in an unpredictable way over time. Some important terms are related to random process are sample function, one outcome of the random variable of function. Some important terms are related to random process. State space, all possible values the process can take. Time domain, time is instant at which the process is observed. Deterministic versus random. Deterministic is predictable. Random is unpredictable. Random processes are used in model real worlds or uncertainties. Applications including communication systems, thermal noise, short noise, channel feeding, interference in wireless communications, control systems or random distributions, measurement uncertainties, system stability, A and also AI machine learning, time series forecasting and prediction of models and future extraction. This application shows why random processes are fundamental topics in engineering. Random process can be broadly classified into three types based on time, discrete time, and continuous time. Based on state, discrete and continuous state. Based on stationary, stationary and non-stationary. And based on stationary discussing process, there is text properties are stationary and non-stationary. Classification of by time and state. Discrete time. Observe process defined only at a specific discrete time is example as stock price at the end of each trading day by day, temperature reading, number of packets are received per second. Continuous time process. The process is defined for all time instants within an interval. Example of voltage fluctuations in circuits and audio signals, temperature variations over time. Discrete random process varies only be for countable exemplary integrates and finite sets and continuous state process values can be a real number with a range or uncountable set. Classification by stationary process or time variant, non-stationary process time variant. Discrete state process or values comes from the countable state and examples are number of packs per variables and continuous. So, continuous state process of values are in continuous range. Example, temperature and voltage signals. The classification by stationary process are statistical properties mean variance autocorrelation remains constant over a time. Strict stationary all probability distributions are in time invariant for any time shift. The joint distribution x of t is equal to the joint distribution of x of t plus tau. Y is stationary WSS only the mean and autocorrelation functions are time invariant, weak weaker conditions than SSS, but sufficient for many applications. Non-stationary process is a statical property changes over time, mean and or variance are functions of time. Time dependent mu of t represented by mu of t and varies with time and causing the process to drift or trend. Time dependent variance sigma square of t changes over time and indicating the varying uncertainty levels. Mean lines in the slope over curve and variance increases or decreases over time. Key properties mean lies in flat variance and remains constant throughout the observations of period. It versus non-deterministic process. Observe the table and character deterministic process and non-deterministic process and definition. Deterministic process are completely predictable and predictability is high. And examples of pure sine wave and exponential decay and polynomial function characterization is described by explicate and mathematical equations. Non-deterministic is uncertain outcomes and defined by probability and low probabilistic and uncertainty outcomes and thermal noise and random brain motions for examples for this non-deterministic process and characterization is described by probability and distributions and statistical problems. Deterministic examples are sine waves x of t as of sine omega t plus exponential delay and polynomial. Non-deterministic are noise signal, random fluctuating in circuits and a random walk, unpredictability path with probability steps and predictable movements in fluids. Real world examples, electronic circuits, random noise in electronic components and thermal noise and hot, short noise and flicker noise and limited in sensitivity of receivers and amplifiers in a communication system. Mobile networks, signal strength variations and fading and multiple path of programmation environment abstracts and gases unpredictable signals and attenuates in wireless communication channels and financial modeling, stock price fluctuations and market dynamics and investors behavior create random variable in assignment prices and requiring from weather data. Variable model weather data, the variations in temperature and rainfall. Each this shows unpredictable behavior, so random process models are used. And distribution functions EDF is defined the cumulative distribution function CDF denoted as fx of x gives the probability that a random variable x takes a value less than or equal to 0. Mathematical function fx of x is p of x is less than of x. This represents the cumulative probability up to value of x for continuous random variables. It's integral probability of density function. Key properties. non-decreasing, and fx of x is mostly non-decreasing if x1 less than x2, then fx of x1 less than fx of x2. Boundary values: fx of minus infinity tends to 0, fx of minus plus infinity tends to 1. Right continuous. Fx of x is the right continuous at every point. Probability range 0 less than fx of x less than 1 for all x. But observe this normal curve standard deviation. Character of S-shaped CDF curve. CDF is used to analyze discrete random process mathematically. Density function. Define the probability density function. PDF denotes as fx of x. Describe the relative likelihood for a continuous random variable. Take and give. It represents the probability per unit length and RAM. The relationship to CDF fx of d by dx fx of x is PDF derivative on CDF with respect to x, and integral relationship on fx of x is in my integral of fx into fx u into du. The CDF is integral of PDF for minus infinity to x. Key properties are non-negative, and fx of x is greater than or equal to 0 for all x. Total area is equal to 1. Key statistical problem. A random process is characterized by the fundamental statistical properties that are describe their behavior and enable systems and analysis and design. Mean, expected value, and variance and autocorrelation. The average value or set central tendency of the random process to give the time instance, and u of x of t is the expectation of x of t in integral x into fx of x dt. Significance is indicates the DC component or basis of process for a WSS process. The mean is constant over a time. Sigma x of t is the expectation of t minus u of x of whole square and x of t into u of x of 2t. Sigma represents the AC power or energy of the process. Higher variance indicates a greater uncertainty and influence. Autocorrelation function measures the statistical correlation between two points in the process. Rx of tau into expect of ex of t into expect ex t plus tau. For WSS, Rx of 0 equal to expectation of x2 of t. Significance: the described memory of the temporal dependence in processor delay rate indicates and how quickly correlation dimensions. Summary of and conclusion to key concept of this definition of fundamental or classification framework and probability functions.